The objectives of this topic are use like bases to solve exponential equations, use logarithms to solve exponential equations, use the definition of a logarithm to solve logarithmic equations, use the one-to-one property of logarithms to solve logarithmic equations, and solve applied problems involving exponential and logarithmic equations. So this is especially powerful if b to the m equals b to the n, then m equals n. So if we have the same base, the exponents must be equal. So our goal is to rewrite the equation in this form, then set the exponents equal to each other, and solve for the variable. So 5 to the 3x minus 6 power equals 125. It would be really nice if we could express 125 as a power of 5. And sure enough, we can. 125 is 5 cubed. This is great. We have the same base. We know that the exponents must be equal to each other. 3x minus 6 equals 3. Add 6 to both sides to get 3x equals 9. Divide both sides by 3 to get x equals 3. The solution set is 3. So as long as we can get both sides with the same base, we can use this strategy. 8 to the x plus 2 equals 4 to the x minus 3. Well, 8 isn't 4 to some power. Is there some base that these numbers have in common? Yeah, sure there is. The base of 2. 8 is 2 cubed. 4 is 2 squared. What do we do now? We don't have the same base yet. Power raised to a power, we multiply the powers. So 3 times the x plus 2. 2 times the x minus 3. Then set the exponents equal to each other because we got the common base of 2. 3 times x plus 2 is equal to 2 times x minus 3. Distribute 3x plus 6 equals 2x minus 6. Add 6, or sorry, subtract 2x from both sides. That gives us x plus 6 equals negative 6, and then subtract 6 from both sides. X equals negative 12. So our solution set is negative 12. So that was using common bases to solve exponential equations. We could also use logarithms to solve exponential equations. If we isolate the exponential expression, Then we could take the common log on both sides of the equation if we have base 10. And we can take the natural log on both sides of the equation for bases other than 10. Then we'll simplify using one of the following properties. Either the natural log of b to the x equals x times natural log of b, or natural log of e to the x equals x, or log of 10 to the x equals x. I hope you followed that. Don't worry, I will break it down. We'll solve for the variable, and then we'll have our answer. So here's what all that meant. Let's use this to solve 5 to the x equals 134. We know how, and hopefully we're really good at solving for x when x is a thing that is with numbers, not in the exponent. When it's in the exponent, we can't do anything. We can't get it by itself. So let's just take the natural log of both sides. Why don't we fuss around with a base 5 logarithm? Well, because we can't calculate with a calculator a base 5 logarithm without the change of base formula. So let's just cut right to it and use the natural log. We'll write natural log of 5 to the x equals natural log of 134. Now remember our properties of logarithms. An exponent can become a coefficient. So we're going to take that x from the exponent and we're going to make it a coefficient. And now x is a thing we can solve for. Divide both sides by natural log of 5. X is equal to the natural log of 134 over the natural log of 5. That we can put into the calculator. That gives us approximately 3.04. But if we want an exact answer, we leave it in terms of the natural log of 134 over natural log of 5. Let's solve 10 to the x equals 8,000. Well, we can do regular common logs on our calculator. And the regular common log will cancel out the base 10. So here, we'll take the common log of both sides. Log 10 to the x equals log 8,000. Once again, an exponent becomes a coefficient. And log of 10 is 1. Or we can just think of that as the log and the base 10 canceled each other out, leaving us with x as a real number looking thing and not an exponent. On the other side, we have log of 8,000, which we can do with our calculator. We get approximately 3.90. But if we wanted the exact answer, we would leave it in its log form, log 8,000. Three to the 2x minus 1 equals 7 to the x plus 1. It'd be real nice if we could use our same base, set the exponents equal to each other form, but unfortunately there is nothing shared base-wise with a 3 and a 7. So we'll take what we have, and we'll take the natural log of both sides. Then exponents become coefficients. And here the entire 2x minus 1 in parentheses goes in front of that log on the left. The entire x plus 1 in parentheses goes in front of that log on the right. Now here's where it gets fun. We want to distribute the natural logs. So 2x times natural log of 3 minus 1 times natural log of 3 equals x times natural log of 7 plus 1 times natural log of 7. Why are we doing this? We had to get those x's out of parenthesis jail. Now we can get x's on one side, things without x's on the other. Let's subtract x natural log of 7 from both sides and add natural log of 3 to both sides. That moves things around to where we need them. Our x's are now all on the same side. They're not in parenthesis jail anymore. Let's factor that x out on the left. Let's put everything else in parenthesis jail. See how they like it. When we factor out an x, we get a leftover piece of 2 natural log of 3 minus natural log of 7. Finally, to get that x by itself, divide by 2 natural log of 3 minus natural log of 7. And there's our exact answer for x. And we can put every bit of that in our calculator and get an approximation of x equals, or x is approximately 12.11. But as far as what x equals, as far as the solution set, keep it in natural log form for an exact answer. So that was fun stuff about solving exponential equations. What about solving logarithmic equations? What about equations with log in them? Well, in all those instances where the log or the natural log helped us get rid of exponential and bring the x down as a coefficient, we're going to be able to use common bases and raise logs as powers to get our x's out of inside logs and able to be solved for. So we want to get the log by itself. And then whatever base log we have, raise both sides as powers of that base. The base and the log will cancel each other out. Solve for the variable. We do need to check our answers here because remember, we have a restriction on what can go inside the log function. The log function only takes positive numbers, no 0, no negative. So let's solve log base 2 of x minus 4 equals 3. Well, the base is 2, the exponent is 3, and that'll be equal to x minus 4. How did I get that so fast? Well, I kind of cheated and used the logarithm as an exponent rule. The logarithm was equal to 3, so I knew 3 was the exponent. I know that 2 is the base. I know that's equal to what's left. But I could also raise both sides as powers of 2. 2 to the log base, 2 cancels out on the left side, leaving us with just x minus 4. We get 2 to the 3 on the right side. 2 to the 3, 2 cubed equals x minus 4. That's where we are. 2 cubed is 8. 8 equals x minus 4. Add 4 to both sides. We get x equals 12. Check. Plug in 12. 12 minus 4 is 8. Since 2 cubed is 8, it is true that log base 2 of 8 is 3. We have a true statement. 12 is the answer. Let's take a look at this one. Solve 4 times the natural log of 3x equals 8. We want to get the natural log by itself, so we need to start by dividing both sides by 4. The natural log of 3x equals 2. Now, right now, our x is trapped inside that natural log. We can get rid of it by raising both sides as powers of e. E to the natural log of 3x equals e squared. The e and the natural log will cancel each other out, leaving us with 3x. And we'll have e squared on the right. Or we can write that as e squared equals 3x. The base is e, the exponent is 2, and it's equal to what's left. Two ways to think about how we get that. Divide both sides by 3. X equals e squared divided by 3. Let's check that value. 4 times natural log of 3 times x would be 3 times e squared over 3. The 3's cancel, just leaving an e squared in there. 4 natural log of e squared equals 8. That coefficient can become a power. E squared to the 4th would be e to the 8th. Natural log and e cancel each other out, leaving us with 8 over 8, or 8 equals 8, which is true. Or, as they did it here, the natural log of e squared, the natural log and the e cancel out, leaving us with 2. 4 times 2 is 8. I took the 4 up as an exponent and did the work from there. We can leave the 4 down and turn the 2 into a number. It all depends on when you want to cancel. Anyway, this checks. That is the answer. The solution is e squared over 3. Let's take a look at this one. And all the work is here. We have log of x plus log of x minus 3 equals 1. The log of x plus the log of x minus 3, we're adding 2 logs together. We can condense that with the log of a product. So the log of x times x minus 3. Raise both as powers of 10. 10 to the log x times x minus 3. 10 to the first. That gives us 10 to the first equals, when the 10 and the log cancel, x times x minus 3. Or think a logarithm is an exponent. The base is 10. The exponent is the log is 1. So 10 to the first on one side, what's left is x times x minus 3 for the other. No matter how you get there, 10 to the first is 10. And we want to distribute that x to get rid of the parentheses. We want to get everything on one side, 0 on the other. We want to factor. We want to solve. We get x equals 5 or x equals -2. And maybe you're in the habit by now of just moving on once you get an answer. But I've been very careful to check these. When we check 5, we get log 5 plus log 5 minus 2 equals 1. Or sorry, 5 minus 3 equals 1. 5 minus 3 is 2. So log 5 plus log 2. That's the log of the product, log of 5 times 2, which is the log of 10, which is 1. That's a true statement. 5 works. But when we plug -2 in, we get log of -2 plus log of -5. And neither of those two things exist. We can't take logs of negative numbers. Now, it wasn't because x was -2 that we threw it away. It was because when we plugged -2 in, we got a log of a negative number. But it doesn't check, so it's not part of the answer. The answer is just x equals 5. Now, just like we had that rule where we can get common bases and set the exponents equal to each other, we can do the same thing with common-based logs. So if the base of the two logs are the same and we have log equals log, then the two things inside the logs must be equal. So get log equals log, set the insides equal to each other, and solve for the variable. Then again, be sure to check, because we can only take logs of positive numbers. Natural log of x minus 3 equals natural log of 7x minus 23 minus natural log of x plus 1. We can condense on the right. Natural log minus natural log is natural log of the quotient. First minus second, top minus bottom. Top is 7x minus 23, the bottom is x plus 1. Now that we have natural log equals natural log, the same type of log on both sides, the insides must be equal. So x minus 3 equals 7x minus 23 over x plus 1. Multiply both sides by x plus 1, that's foiling on the left. X plus 1 times x minus 3. On the right, the x plus 1's cancel out, just leaving us with the 7x minus 23. When we did FOIL those two, we got x squared minus 2x minus 3. Get everything on one side, 0 on the other. X squared minus 9x plus 20 equals 0. We can factor. We can solve. We get x equals 5 and x equals 4. We must check x equals 5 and x equals 4. Factoring, right? When we check 5, natural log of 5 minus 3 equals natural log of 7 times 5 minus 23 minus natural log of 5 plus 1. 7 times 5 is 35. 35 minus 23 is 12. So we have the natural log of 2 equals the natural log of 12 minus the natural log of 6. Take quotients on the right to condense that into a single natural log. Natural log of 12 over 6, which is 2. We have the natural log of 2 equals the natural log of 2, so that one checks. Plugging in x equals 4. Natural log of 1 equals the natural log of 28 minus 23, which is the natural log of 5, minus the natural log of 5. Natural log of 5 minus natural log of 5 is 0. The natural log of 1 is 0. 0 equals 0 is a true statement. So it is a solution. So the solution set is 4 and 5. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So remember, we have this compound interest formula. A equals P times 1 plus R over N to the NT. If we plug in what we know into this formula, the principal is 1,000, that's P. The end amount, we want it to be 3,600, so that's A. R will be 8% as a decimal, so 0.08. Compounded quarterly means that there are n equals 4 compound periods per year. T is what we don't know. How long is the question that's being asked? We know everything except T. So let's simplify. Inside the parentheses, 0.08 divided by 4 calculates to 0.02. 1 plus 0.02 is 1.02. We cannot multiply that by 1,000. There is a lock on 1.02, a lock called 4t. To get that t by itself, we need to get that 4t by itself, and not just by itself, but out of the exponent. And to do that, we have to get the 1.02 to the 4t by itself. So we need to get rid of multiplying by 1,000. We divide both sides by 1,000. 3.6 equals 1.02 to the 4t. Now let's just take the natural log of both sides. That is our tool to make an exponent a coefficient. So that 4t goes from the exponent to the coefficient. We can divide both sides by 4 natural log of 1.02 to get that t by itself. That is the exact answer. But if we put those pieces in a calculator, we would get 16.2, which we have to do because the question specifically says to the nearest tenth of a year. So we need to round to the nearest tenth. 16.2 years is what it'll take for this 8% quarterly compounded growth to take $1,000 to $3,600. The percentage of adult height attained by a girl who is X years old can be modeled by f of x equals 62 plus 35 log x minus 4, where x represents the girl's age from 5 to 15, and f of x represents the percentage of her adult height. At what age has a girl attained 97% of her adult height? Well, take our function. We want to solve for x, which means we got to get that x minus 4 by itself, which means we need to get it out of the log, which means we need to get the log by itself, which means we need to get the 35 log by itself, which means we need to get rid of that positive 62. And that is equal to f of x, which is 97 in this particular problem. So we subtract 62 from both sides. 97 minus 62 is 35. That's nice. Because now to get rid of multiplying by 35, we have to divide by 35, and 35 divided by 35 is just 1. Now to get the log by itself, well, we've done that. To get rid of the log, we need to raise it as a power of 10, because then the 10 to the and the log will cancel each other out. Or you can think of it as a logarithm is an exponent. This log is 1, the exponent is 1, the base is 10. 10 to the first equals x minus 4. So 10 equals x minus 4. Add 4 to both sides. X equals 14. So at approximately age 14, a girl has attained 97% of her adult height. And that is it for this topic. Let's say we had something like 3 to the 2x minus 6 equals 81, where the x that we want to solve for is in the very top, in the exponent. Well, if we can get it so both sides are the base raised to a power, the same base raised to a power, which we can do here, because 81 is 3 to the 4th. This implies that the exponents are equal. 3 to this equals 3 to that, this equals that. I'm going to break that down in a little more detail when we're done. Add 6 to both sides. Divide both sides by 2. We get x equals 5. The reason this works is because we're allowed to take the log of any base of both sides. So the extra steps here that we don't need to show because it's implied are that we're taking the base 3 log of both sides, then the powers are coming down front as multiplication. The base 3 log of 3 is 1, because 3 to the first power is 3. So 2x minus 6 times 1 equals 4 times 1.
which gives us 2x minus 6 equals 4, which we solved to get x equals 5. So what's really happening is that we can take the log of both sides. And it doesn't matter what kind of log it is. Here we use the base 3 log because it helps us get rid of the base. But in general, we're allowed to take any log of both sides. So keeping that in mind, let's say we have 5 to the 5x plus 6 equals 4 to the 8x. And we're given the direction, use natural logs. What that's telling us is your first step is to take the natural log of both sides. Ln of 5 to the 5x plus 6 equals ln of 4 to the 8x. Well, then what would we do? Well, we have powers inside our logs. The powers come out front as multiplication. 5x plus 6 times the natural log of 5 equals 8x times the natural log of 4. We want to get all of our x terms on one side, everything without an x on the other. We also need to get rid of the parentheses first so we can distribute the natural log of 5. 5x natural log of 5 plus 6 natural log of 5 equals 8x natural log of 4. I'm going to subtract 8x natural log of 4 from both sides. That got everything on the left. I'm going to keep the 5x natural log of 5. I'm going to keep the minus 8x natural log of 4. But I'm going to subtract the 6 natural log of 5. And you'll see why we're getting all the x's on one side in just a second. But this would leave 5x natural log of 5 minus 8x natural log of 4. Subtracting this over, so this equals negative 6 natural log of 5. Let me move this up. Give myself more room to work. Okay. Now, since we got everything with an x by itself on the left, that means everything has an x on the left. That means we can factor an x out, and we're left with 5 natural log of 5 minus 8 natural log of 4. And we can divide both sides by this factored piece, leaving us with just an x. Now, if you have a calculator with a natural log button, you can find the decimal approximation here. But this is what I'm looking for. X equals, and then everything written in terms of logs. The problem is we don't like that we have the negative. In fact, we would prefer that the top is positive. So I'm actually going to go ahead and uncircle this because we're not in final form yet. If this was a multiple choice test, you'd get this far and you'd realize, oh, that answer is not there. The negative can go on the top or the bottom. We're going to put it on the bottom. So we can't just write negative and the rest of it. The entire bottom has the negative. Top's positive though, so we're almost done. Distribute the negative. -5 natural log of 5 plus 8 natural log of 4. Whoops. Let me write this up here, give myself more room. This is tough, but this is on the final exam. Okay. So I distributed the negative on the bottom. Plus 8 natural log 4. And now the bottom can be rewritten. Since it's negative plus this, we can switch the order of addition so that it's 8 natural log of 4 plus a negative, which is just minus 5 natural log of 5. We don't like starting with our negatives. And that is the final form. And in a calculator, this ends up being approximately 3.1732. But that's not what I'm looking for. I'm looking for the natural log form. X equals this in terms of natural log. Let's look at one more natural log, or one more logarithmic equation. Also on the final exam, a problem like this. Okay, our strategy. In the last one, we wanted to get the x by itself, but it was in the exponent. We ended up taking natural logs of both sides to get rid of that. Here, the x is inside a logarithm. And since it's inside a base 3 logarithm, we want to end up getting log base 3 of x minus 5 by itself. with everything else on the other side. And then we're going to raise both sides as powers of 3. That'll get rid of the log. That'll free up our x. You'll see, I promise. So first, let's go ahead and start working towards getting the log base 3 by itself. We're going to subtract 10 from both sides. That leaves us with -2 log base 3 of x minus 5 equals 8 minus 10 is -2. How lovely. We can divide both sides by -2, which gives us our log base 3 of x minus 5 by itself. -2 divided by -2 is 1. I'm going to move this up so I have more room to work. I'm going to raise both sides as power of base 3. Which is the reverse of what we did when the x was in the exponent. That's when we took logs of both sides. Now, if we want to get rid of a log, we need to make both sides exponents. The base 3's cancel, leaving us with just x minus 5, no longer in an exponent. 3 to the first is 3. Add 5 to both sides, and we get x equals 8.
The objectives of this topic are model exponential growth and decay, use logistic growth models, choose an appropriate model for data, and express an exponential model in base E. The mathematical model for exponential growth or decay is given by f of t equals a sub 0 e to the kt, or a equals a sub 0 e to the kt. If k is greater than 0, the function models the amount or size of a growing entity. A sub 0 is the original amount or size of the growing entity at time equals 0, also known as the initial amount. A is the amount at time t, or f of t is the amount at time t. And k is a constant representing the growth rate. All of that is the same for a k less than 0, except for the fact that instead of a growing entity, it's a decaying entity. And k would represent the decay rate. So if k is positive, we have growth. If k is negative, we have decay. An exponential growth model looks like this when it's graphed. It's the positive part of an exponential function. And exponential decay is the positive part of a negative exponential function. Why just the positive parts? Because a sub 0, the original amount, happens when t equals 0, and t is our x-axis here. Time is the input. In 2000, the population of Africa was 807 million. And by 2020, it had grown to 1,341 million, also known as 1.341 billion. Use the exponential growth model A equals A sub 0 e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So start with our exponential growth model. We are given a t equals 0 amount, aka a year 2000 amount of 807 million. So 807 is our A sub 0. When t is 20, aka 20 years after 2000 in 2020, when t is 20, we had a population of 1,341 million. So A is 1,341 when t is 20. Now we need to solve for k. We need to know what our constant of growth or decay is. So to get the e to the 20k by itself, we need to divide both sides by 807. Take the natural log of both sides. Then that 20k goes from exponent to coefficient. Natural log and e cancel each other out, leaving us with just the 20k. Divide both sides by 20. K equals the natural log of 1,341 over 807, all over 20. That would be the exact value of K. But we'd like a number. So we pop that into the calculator, and we get about 0.025. That would be 2.5%, and it's going up. It's positive. It's growth. 2.5% growth. But the function that models the data is going to be the function with our initial A and our K. We're going to leave A and T alone because that's what the function does. We plug in a T and we get out an A. So the model is just A equals 807 e to the 0.025 t. Now we're going to use that model to answer the question, by which year will Africa's population reach 2,000 million or 2 billion? We just found that A equals 807 e to the 0.025 t. We want to know what's the t when A is 2,000. Divide both sides by 807. Take the natural log of both sides. Exponent becomes coefficient. Divide both sides by 0.025, and that is our exact t. So that many years after the year 2000. The exact answer doesn't really help us understand, though, does it? So put it in the calculator. It's about 36. So 36 years after 2000, we predict by the year 2036, Africa's population will reach 2 billion. The half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. So the half-life is the amount of time that it takes for there to be half of the thing remaining. Find the exponential decay model for strontium-90. So our general model, A equals A sub 0 e to the kt. We know that half of the initial amount, A sub 0 divided by 2, is what we're looking for. This actually all shakes out to 1/2 equals e to the 28k. We were given a t of 28. That's where the 28 came from. But the way half-life works out, always, is that it'll shake out to 1/2 equals e to the kt. Because if we divide both sides of a sub 0 over 2 equals a sub 0 e to the kt by a sub 0, the a sub 0's cancel out, leaving us with 1/2. So 1/2 equals e to the kt, 1/2 equals e to the 28k. We have an e by itself, so let's take the natural log of both sides. Natural log of 1/2 would equal 28k. Divide both sides by 28. There's our k. There's our decay constant. But we'd like a number. So we put that in the calculator, and we get approximately negative 0.0248. We knew it would be negative because we're dealing with decay. Plug that and our a sub 0 into the original equation. We don't actually have a value for a or a sub 0, so the only thing we have here is our k. We leave t as t because t is what we would be plugging into this model. The important thing that we found was the k. So we found the exponential decay model. If there are originally 60 grams, how long will it take for the strontium-90 to decay to a level of 10 grams? So how long will it take means we're going to solve for t. Our original amount is 60, so that's our a sub 0. The amount we want in the end is 10, so that's our a. Divide both sides by 60 to get the e by itself. We get 1/6 equals e to the negative 0.0248t. We have the e by itself, so take the natural log of both sides to get rid of it. Natural log of 1/6 equals negative 0.0248t. Then to get the t by itself, divide both sides by negative 0.0248. That's our exact value for t. That many years. course, that's useless in terms of giving someone some reasonable information that they can digest quickly and easily. So we throw it into a calculator, and it's about 72. So about 72 years is how long it would take. Now, that was exponential growth and decay. A logistic growth model is given by f of t equals c over 1 plus a times e to the negative bt, or a equals c over 1 plus a times e to the negative bt. So a, b, and c are all constants here. In a learning theory project, psychologists discovered that f of t equals 0.8 over 1 plus e to the negative 0.2t is a model for describing the proportion of correct responses f of t after t learning trials. Find the proportion of correct responses prior to learning trials taking place. So we have our model. Prior to learning trials taking place, there would be 0 trials. So t would be 0. We're plugging 0 into this function. How do we evaluate this? Well, let's take care of the exponent first. Negative 0.2 times 0 is 0. Anything to the 0 power is 1, so e to the 0 is 1. 1 plus 1 is 2. So 0.8 divided by 2, which is 0.4. So prior to learning trials taking place, the proportion of correct responses was 0.4, 4 in 10, 40%. Find the proportion of correct responses after 10 learning trials. Well, now t is 10. Negative 0.2 times 10. Looks like I'm doing this on the calculator. Negative 0.2 times 10. That's negative 2. E to the negative 2 is 0.1353. I'm going to leave that in the calculator and add 1 to it. And I'm going to write down as many digits as I can remember. 1.13533. 0.8 divided by ooh, my calculator will let me type it all in. So 0.8 divided by parenthesis 1 plus e to the negative 0.2 times 10, close parenthesis. I get 0.704. So about 0.7. 7 tenths, 7 and 10, 70% is the proportion of correct responses after 10 learning trials. What is the limiting size of f of t, the proportion of correct responses as continued learning trials take place? The limiting size is going to be the numerator of our logistic growth, 0.8. In example 4, we have this table which shows the populations of various cities in thousands and the average walking speed in feet per second of a person living in the city. We want to create a scatter plot for this data. Now that just means we're going to take each pair of information and turn it into an ordered pair that we can put on a graph. So here the population in thousands is the x-axis. The walking speed is the y-axis. Notice the shape that's happening here. What kind of curve that we've studied, that we're currently studying, looks like this? The log looks like this. So y equals a times b to the x in base e is y equals a times e to the natural log of b times x. We're going to use this fact to rewrite a model in base e. And looking at this, this makes sense because the e and the natural log cancel each other out, just leaving us with a regular b. We want to rewrite 4 times 7.8 to the x in terms of base e, express the answer in terms of a natural logarithm, and then round to 3 decimal places. So our b here, we're going to rewrite as e to the natural log of 7.8. And that'll be times x. We want to express the answer in terms of a natural logarithm. That is what we have done. And now we're going to round to 3 decimal places. The natural log of 7.8 is 2.0541. So 2.054 times x. And that's it for this topic.